Today we're going to be looking at Learning Target 3D, which is creating a graph to represent a function. Remember, as part of this unit, we're really looking at algebraic connections between tables, graphs, equations, and words and/or pictures. Your last learning target really focused on how to create equations from the other pieces. Today we're really looking at how to create the graphs. Let's start by talking about function notation. This is a new way of looking at an equation. We use function notation as a way of clarifying what values are getting plugged in for x in an equation. Instead of using a table of values, we can write equations in function notation and evaluate the equations for certain values. If you remember that f of x is essentially the same as y in an equation, that may help you in solidifying your understanding. As we look at function notation, this is what it looks like. In the red, we have an equation which says f of x is equal to 2x plus 4. We're then going to ask what would f of 3 be and what would f of negative 2 be. Notice that the f here and the f there correspond with each other. So we know that this 3 and this negative 2 is going to get plugged in for x in the f function. Same thing down below. We have g of x equals negative 3 times x. So we know that this 5 will get plugged in for x in the g function, and that negative 4 will also get plugged into x in the g function. The first step is simply to plug in those values into x. Once the value is plugged in, we just go through and solve. So here we end up that f of 3 is equal to 10 when we solve that. We get f of negative 2 is equal to 0. G of 5 is equal to negative 15, and g of negative 4 is equal to 12. Being able to plug values in and use function notation is very important if we're going to be able to graph from function notation. So let's look at an example. We want to graph this equation at h of x is equal to x minus 4. We start by just plugging in values for x. So I plug in 0, so h of 0, when we plug it in and solve, we get the answer of negative 4. So we have the point 0, negative 4. That corresponds to this green dot on the graph. Pardon me, the purple dot on the graph. We now plug in 1 to our function. H of 1 would equal negative 3. So we have the point 1, negative 3, which corresponds to the red dot on the graph. Plug in 2. H of 2 would equal negative 2, which corresponds to the green dot on the graph. Once we have these 3 points, we can see the general trend. So we can draw our line to represent the equation. Since this is an equation, we know that it continues on forever in each direction. So that line extends on forever, as indicated by the arrows on each side. Let's now look at how to graph from a table. Again, we're using function notation. Thus we have x and f of x. However, the graphing is very similar to what you've been doing with y. So, when we plot these points, negative 2, 3 is the green dot, negative 1, 5 is the yellow dot, 0, 7 is the red dot, and 1, 9 is the gray dot. Since this is not an equation, we cannot assume that it will continue on, so we just leave it as a discrete situation. Let's look at a piecewise function. The piecewise function is very similar to what you've been doing, earlier in the year when you graphed my situation around the room. As I moved around the room, you graphed my distance from the door. For this situation, we're going to let time be the independent variable and distance from home be the dependent variable. For this, we're going to graph this situation. Mr. Braychek decided to walk his dog after school. He left home and walked away from his home for 15 minutes, then turned around and walked back. 5 minutes after he returned home, he realized he needed something from the store and drove to the store, spent 30 minutes shopping, and drove back home. Let's look at what this graph would look like. Again, our independent variable is time, and our dependent variable is distance from home. You can see here from the steepness of this line that I'm not walking very fast. I walk away from home, turn around and walk back home. I then drive to the store. Notice that the steepness of this line is much steeper than that line because driving covers more distance as less time goes by. I then spend 30 minutes at the store, so my distance is not changing but time is still going by. I then drive back home. The steepness of this line is about the same as the steepness of that line because driving would cover about the same amount of distance in the same amount of time. Here are a couple of practice examples for you. The red, we want you to graph this equation, g of x equals 2x minus 4. And in the purple, create a graph of the table. Pause the video now, as the solutions will be on the next slide. Notice that your g of x is an equation, thus it has to be represented by a line. The original equation was g of x equals 2x minus 4. So our y-intercept is at negative 4, and we're climbing up 2 over 1, up 2 over 1. You could also find those points by plugging in values for x and finding your value for g of x, and then creating that trend line. H of x, remember, was a table of values. So we can't create a line to represent that situation. We keep it as discrete. So by plotting the points, you end up with the purple dots seen there. Let's look at a practice piecewise situation. Graph the following situation. Let time be your independent variable and speed be your dependent variable. Mr. Dunn was driving to Seattle going 100 miles per hour. Approximately 30 minutes into his drive, he was pulled over by a policeman and ticketed. Following the traffic stop, he continued driving at 70 miles per hour. 2 hours into his drive, he stopped for gas, then continued his drive to Seattle going 80 miles per hour. Pause the video now until you have a chance to graph this. We will then look at the solution. Here's the solution to that situation. Notice, at first, his speed is up here at 100 miles per hour. When he gets pulled over, he has to decelerate or slow down really quickly and stops and waits for the ticket. He then accelerates back up to the 70 miles per hour, which he drives for a period of time. In order to stop to get gas, he must again decelerate and stop. Time goes by while he's filling up for gas. He then accelerates back up to the 80 miles per hour and continues his drive to Seattle. We are going to be looking at some situations, both piecewise and with function notation, when we have school next week. So please make sure you come with any questions and ready to practice this skill.